All right, so picking up where we left off here, number 6, partial fraction decomposition. It's something that we've talked about in great length on Wednesday. And we're going to go back and get these. So, where we want to begin each of these problems, remember, is I'm looking at negative x plus 4 over x squared plus 6x plus 8. We're trying to figure out what this is going to be in terms of some fraction plus some other fraction. This is what we're going to. So again, the place where we want to begin each and every time is we want to see about factoring the trinomial in the denominator here. So again, we're hoping, again, we always have our fingers crossed, but we're hoping for a cancellation to occur that will really simplify things. So again, when I'm looking at the x squared plus 6x plus 8, I know that's going to factor x plus 4 times x plus 2. And even though it's close, no, we do not have the ability to cancel. Again, I do not have common factors as my numerator is negative x plus 4, denominator is positive x plus 4. So again, not the same, cannot cancel. So again, what we're going to claim is that once we have factored that denominator, we know that my denominator is over here, x plus 4 and x plus 2. We need to go about targeting and finding the numerator. So again, we're going to, back to my answer, we now know that those denominators, x plus 4 and x plus 2, we need to go about, like I said, targeting and finding a and b. So what we would want to start with here is we're looking at this mess. We have a whole bunch of fractions, and if we could clear some fractions, that's going to be in our interest to do so. So again, if I were to rewrite this, just recopying what we have. Again, on the left side, if I were to multiply by the denominator, x plus 4, x plus 2, again, that's going to create the cancellations that we're seeking, but the catch is that we have to do the exact same thing on the right side to all terms. So x plus 4, x plus 2, over here, times x plus 4, x plus 2. Right. All right, now the reason for doing this is that the x plus 4's will cancel, and the x plus 2's will cancel, leaving me on the left side with a negative x plus 4. On the right side, we initially going to have the x plus 4's cancel, leaving me with a times quantity x plus 2. And then my secondary term here, the x plus 2's cancel, leaving me with b times the quantity x plus 4. Now remember that we refer to this as our model, and we're going to use this model to solve for a and b. While systems of equations would be an option, again, we can essentially utilize shortcuts here. So we want to find a, and then later on we're going to find b. Now, when we begin here with finding a, understand what we really want to do. Again, we call it finding a, and that's ultimately the goal. What we really want to do is cancel b. So how could we go about canceling b? And I'm looking right there at the x value. If we were to let x equal negative 4, I think that should do the trick. Because if I let x equal negative 4, within the parentheses, negative 4 plus 4 is 0, and b times 0 is 0. That cancellation occurs, and we're in great shape. So again, I'm plugging back into my model of negative x plus 4 is equal to a times x plus 2 plus b times x plus 4. And everywhere that we saw an x, we are now going to insert a negative 4. Because that's what we're allowing x to equal. So as we allow x to equal negative 4, on the left side, negative 4, positive 4 plus 4 is 8, is equal to a times negative 4 plus 2 is negative 2, plus b times negative 4 plus 4 is 0. And that's what we were hoping would occur. B times 0 is 0. It's canceled. It's gone. We now have a little bit more space here. We now have 8 is equal to negative 2a. And to isolate a, dividing both sides by negative 2, we've done it. We found that a is equal to negative 4. Now, again, not our final answer or anything, but if a is negative 4, we now know back at the beginning what we're going to plug in place here for a, which is going to be the numerator over the a plus 4. So we know that a is negative 2. So now we focus on finding b, and in a very similar fashion, when it's time to find b, what we really are going to be doing, or going about doing, is we're going to try to cancel a. So in a very similar fashion, we want to be able to see the model, we're going to cancel A by plugging a specific value in place for x that's going to cause that cancellation. So in this particular case, looking at my parentheses, x plus 2, if I were to allow x to equal -2, that should do the trick. So, split here. Again, plugging back in my model of negative x plus 4 is equal to a times x plus 2 plus b times x plus 4. And everywhere that we saw an x, we are going to put a -2. Cleaning this up, on the left side, -2 is positive 2 plus 4 is 6 is equal to a times -2 plus 2 is 0 plus b times -2 plus 4 is 2. As we were hoping, a times 0 is 0, it cancels, and 6 is equal now to 2b. Dividing both sides by 2 enables us to say that b is equal to 3. So in a very similar fashion, b is not equal to 3 as a final answer, but now that we know, going back to our beginning stages, b was representing the numerator in the fraction with the denominator of x plus 2. So now if we said that b is equal to 3, we are in a position to where we can say that we have completed our partial fraction decomposition. All right, so the last type of problem that we wanted to see, trying to go full screen here. Again, the major focus is to understand that yes, this is a linear programming problem, but it's not an entire problem. We are not asking you to go full on and do the entire thing here. The entire thing would allow, or would force us, I should say, to define variables, create an objective function, create the constraints, graph the constraints, shade appropriately, find the vertices, plug your vertices back into your objective function to optimize, and that's how we would finalize our answer. Here, we're able to kind of stop in the middle, probably less than the middle. I'd say we're doing about 1/3 of that work here. We still want to set everything up, but once we've created the constraints, then we're done. All right? Again, we do not have to solve this problem. So, reading through, it says that the lipid portion of a diet is to provide at least 475 calories, 62 units of vitamin A, 94 units of vitamin C. All right, so every day that's what we're supposed to obtain at a minimum. Cup of dietary drink X, it costs 17 cents, provides 90 calories, 32 units of vitamin A, and 24 units of vitamin C. Cup of dietary drink Y costs 20 cents, also provides 90 calories, 21 units of vitamin A, and 31 units of vitamin C. So here's where they're actually telling us what to do. The question here, how many cups of each drink should be consumed each day to obtain an optimal cost and still meet the daily requirements? All right, so the first thing that has to happen is we need to define the variables. So I'm going to go with X and Y. We're going to let X be the number of cups of drink X. Similarly, we're going to let Y be the number of cups of drink Y. Now, please understand that I'm doing more here than just saying that X equals drink X, Y equals drink Y. It's the number of cups. Again, we could have a different problem on our hands if we were going with the number of gallons or the number of ounces or the number of, again, this case, we're looking for the number of cups. All right, so now the objective function. Again, kind of key in here on this last, what we were trying to do is we were trying to create an optimal cost. Optimal cost, that means that my objective function, that's what we're trying to optimize. So we're trying to optimize the cost. So again, we're talking money here. We don't know how much, or how many, I should say, how many cups of drink X we are going to consume or purchase, or however we want to put this. But we do know that each one is going to cost us 17 cents. Similarly, we don't know how many cups of drink Y we are going to consume, but we do know that each is going to cost 20 cents. So when we're creating the objective function, there it is. Now for our problem, right here, number 7, all we have to do is create the objective function. We aren't actually going to use it. But if this were a full problem, which we will have to do some of this on the multiple choice portion, not on the performance portion. But again, if this were one of those situations, then like I said, we could have a little bit more on our plate, so to speak. All right, now coming up to the constraints. Again, we don't want to get mixed up here. we are going to create a constraint dealing with calories. We're going to create a constraint dealing with vitamin A and a constraint dealing with vitamin C. Okay, so vitamin A, this is what we had, or excuse me, calories is where we're going to start here. Calories is what we had going on in red. We, again, do not know how many cups of drink X we're going to consume, but each one is going to provide 90 calories. Similarly, we don't know how many cups of drink Y, but each is going to provide 90 calories. Now, paying particularly close attention to the beginning sentence here. It says the liquid portion of a diet is to provide at least, again, key phrase here. We have to have at least 475 calories, which means that more is okay. We have to have at least 475 calories. So for that reason, my 90x plus 90y has to be greater than or equal to 475. All right, now, basically doing the exact same thing here with vitamin A, all the stuff that we have underlined in green. We are going to obtain 62 units per cup of drink X, and we are going to obtain, no, I am sorry, I looked at our daily requirement. We are going to obtain 32 units per cup of drink X and 21 units per cup of drink Y. We have to have at least, so greater than or equal to, 62 units of vitamin. For vitamin C, what we have underlined in blue, each cup of drink X is going to provide 24 units of vitamin C. Each cup of drink Y is going to provide 31 units. We have to have at least, so greater than or equal to, 94 units of vitamin C. Now on the surface, it may seem like we're finished. It may seem like we have all of our constraints and we're done, but please don't forget about what we always refer to as our obvious constraints. We know that even if drink X is the most disgusting, putrid thing that has ever existed, that it's literally impossible for you to consume a negative amount of drink X. So for that reason, X has to be greater than or equal to 0. Similarly, Y has to be greater than or equal to 0. But these are our constraints. And for our purposes, here on number 7, we're done. We don't have to go any further. We don't have to put this into a graphable form. We don't have to graph it. We don't have to find any shading or vertices. And we definitely don't have to plug anything back into the objective function. Okay? So like I said, we are finished here at this point. Again, going with the quick click through, we definitely need to know how to graph a quadratic. We need to know how to graph an exponential. We need to know how to graph a piecewise function. We need to know how to describe transformations. We need to know how to graph a logarithm. We need to know how to do the partial fraction decomposition, as well as the linear programming problem setup. Not the full-on problem, but the setup. Not only do we need to know how to do all of the graphing, but again, the domain, the range, the asymptotes, all of that fun stuff. You guys, I think that we are much more prepared, much more ready than you may initially feel, but we're going to get there. So again, we're going to continue to work and practice with this stuff leading up to our final. But again, should you have any questions, please let me know, and we'll get these things all figured out.